All right, good. I'm glad to give this talk about integrated land cover data for monitoring urban landscape dynamics. My name is George Shan, I work for the USGS AIS Center in Sioux Falls, South Dakota, USA. And so I'm going to give a very general introduction about our center and also remote sensing data for land cover mapping and NLCD, and then our recent land change monitoring assessment and projection LCMAP activities, and also about the summary about this talk. So in general, for the monitoring land cover, we use the remote sensing data to do this we call the heavy duty task. Start a very early year, we use different remote sensing data to monitor land change. So we call the transferring the satellite measurement into the information product for the scientific analysis and decision maker. For example, we can use Landsat data to develop a different product, including the surface albedos, file disturbances, water extent, biomass, land cover, and the leaf area index, slope cover. So you can count on all this related to land surface characteristics and the change information. We can use this Landsat to develop those products. Of course, we can, in early time, we can use other satellite data, including AVHR at the beginning, and then later we can use MODIS to do the same work. MODIS, of course, provide a little bit of coarser resolution for spatial resolution, and the Landsat can provide 30-meter resolution for this product. So at USGS AIS, we did a lot of work, try to use remote sensing data to monitor land surface change. So at the beginning, we developed so-called Anderson classification system, focusing on using satellite data to monitor land cover and land cover change. And after that, we developed so-called first generation of a national land cover database called NLCD 92. And furthermore, we developed the global land cover in 98 from the USGS effort. And after that, we'll continue to this so-called NLCD update, and also develop a new initiative called LCMAP. So I'm going to talk about that one by one. So for the National Land Cover Database, we call it a product suite. For example, in 81, from 2001, we generated this, we call the baseline product suite, including land cover, percent impervious surface, and percent tree canopy cover. So overall, the land cover accuracy is about 85%. And for the land cover, we have 16 different land cover types. And also for the percent impervious, so we classify the urban area, the impervious cover in 30 meters resolution, and provide quantitative measurement for the urban area. And so it's a good example to explain why we use impervious surface to do for the land cover. And on the left is a percent impervious surface. On the right side is our semantic land cover. And you can see when we measure the percent impervious surface, for example, from 1 to 100%, that's percentage impervious cover, we can convert this information to the semantic land cover, like 1 to 19%, we label as 21 called the open space development, and the 20 to 49 we call the low intensity development, and the 50 to 79 we call medium intensity development, and then for 80 to 100% we call high intensity development. So through this way, we can measure the percent impervious and then connect it to the semantic land cover, mainly focusing on urban area from NLCD. So for NLCD continue work, we label this NLCD effort as so-called a 4-pillar effort. And this 4-pillar including spectral information, that's a Landsat pixel, ancillary data, and we use that one to improve our land cover classification. And the shape and the context, we use that additional segmentation information to help us to improve the classification and the succession and the trajectory. That's called a time series. And we make sure our land cover change information follow the succession and the trajectory orders. So in that way, our database can be used to do the change detection and also change comparison for the entire nation. So for the NLCD land cover database in 2016, we developed the land cover and also impervious surface tree canopy. So for this one, we generate the land cover in every 2 to 3 years from 2001 to 2016. So in that way, we can provide consistent comparison for the entire nation. So you can see this is one of the product provided for the NLCD. For the entire nation, we can estimate the land cover change from 2001 to 2016. So this one shows where we have the high intensity change for the land cover, while we can lower intensity change. So for example, on the western side of the US, we have a lot of change occurred in this western area associated with a wetland fire and also some urban development. On the eastern side, we can see the different story. We can see some, for example, southeastern side, we have the forest cut related activities, and then this transfer to the change information. So entirely for the US, we can have the general estimate. For example, for the major land cover classes between 2001 and 16, we can see urban only count 4%, although it's only 4%, but it's still a very important land cover type. And then the largest one still the forest, 48%. And so from the NLCD data, we can just do some general assessment. For example, this one we estimate from agricultural land transfer to the urban, and then you can see agricultural land change. So you can see from this graphics, for most of long cropland to cropland type change occurred in the central part of the US. And also for other type, for example, for crop to long crop type, that's blue. Blue one mostly associated with urban development as well as some forest change in the US. So this is a good example to show. And then for the 2001 to 2016 urban change, this one just shows in each state the proportion of the urban land cover. And you can see for this, from this graphics, we can see in the eastern side, for a lot of states, we have very high proportions of urban, and that's on the left side graphics. And so we can use this graphics shows what is the proportion in the current status in each state. And on the right side is a change rate. For example, from 2001 to 2016, for example, in Texas, we have 14.6%. That means urban growth during that period increased by almost 15%. And other state, for example, in the central of the state, in South Dakota, the state that's only increased about 2.7%. So through this way, we can just tell our general natural resources management team to tell them what is most urban growth occurred, and in the United States. And then surprisingly to say, the most change rate occurred in the Arizona state. So Arizona got a 16.2% increase during this period. And then from this one, we can get the entire US urban development distribution. For example, on the left side, we can see the red color shows 2001 urban, and the green shows 2006 urban, and the yellow shows 2011 urban, and then blue shows 2016 urban. So through this way, you can see the urban development in the entire US. And then if you look at the bar chart from here, you can see that generally we have the key urban area keep growing in the entire United States, but the change rate reduced slightly. So the highest change rate occurred from the 2001 to 2016. After that, the change rate is still above 1.5%, and then from the 2001 to 2016, that change rate dropped slightly, but still a little bit above 1.4%. And so if we can zoom in the different locations, as I mentioned, if we use a different color to show their development, then you can see in different cities. So here I use 3 examples: Dallas, Houston, and Washington-Baltimore area. So these 3 areas shows a different development stage for the urban growing in the US. Okay, so that's pretty much about the NLCD effort. Remember, NLCD provides 30-meter resolution land cover, and in the urban area, we have 4 different classes. And started several years ago, about 5 years ago, USGS developed this new initiative called the LCMAP, Land Change Monitoring, Assessment, and Projection. So this initiative try to build up the system, the software for land change science. We wanted to use this data generated from this system to enable temporal analysis of a large volume of Earth observation data. So that means for the LCMAP, we try to use entire Landsat archive from 1980s to the current, generate annual land change information in 30-meter resolution. So that's the main purpose for this one. So for this one, we wanted to provide information to better understand and document historical land change and monitor and inform about the change as it occurs. So that's general LCMAP effort mission. And this one just gave a very general methodology introduction to tell how we do our LCMAP work. So this one pretty much involved the Landsat, US Landsat analysis ready data, we call it ARD. And so that's the entire Landsat archive we're going to use. And after that, we generate the so-called harmonic time series models to detect the change.
George,
and yes.
George, your 8 minutes is up, even though we started late. Can you wrap up, please?
Yeah, I'm going to go over quickly. Thank you. So we can use this information to estimate the change information for the entire from the entire Landsat archive, and also we can generate the annual land cover. So this is a general, the 10 product we can provide for the from LCMAP. And so I'm going to try to skip this one. We also provide independent validation data to do that way, this work. I want to briefly mention the integration part. So for this effort, we try to integrate the data side from the different sources, including NLCD and other data sources, to generate the different training information for us. And then for LCMAP, we try to integrate with NLCD data, because NLCD only start 2001 and then LCMAP we're going to start early. So we want to use early LCMAP data to integrate NLCD, and then we can get the land cover change, especially for the urban area, to have 4 classes urban annual land cover change. So this is just general graphics to show how this integration works. And in general, this integrate work can help us to get additional land cover information, especially in the urban area. In that way, we can have the 4 land cover classes, and then we can also get annual land cover change for this for urban land cover classes for the different assessment work. I think I already over the time, so I'm going to quickly draw my conclusion. So remote sensing for the national land cover mapping already did a lot of work to generate 30-meter resolution work. And we're going to produce more frequent land cover change to use that information to monitor land cover, including the urban area. And for the future, we're going to look at the land cover change product, provide the near real-time monitoring, including the urban. And also we try to integrate it with different earth science models to do the entire change assessment. All right, good. I think that's all my presentation. Thank you.
Okay, thank you very much. Your moderator is actually here. Xinghao is back. So I'm going to hand off to Xinghao, and I know that you guys have about 8 minutes apiece, and George took more than that. So you guys get to fight over how much time you have left. Reminder to put the questions in the chat, please, so that everybody can see them and the speakers can answer them after they're finished if they want.
Thank you, Casey. Sorry, I missed at the time, actually starting time. I have been working really hard to do this math, but still missed at the time. I'm getting old. Anyway, perfect. Okay, George is just done. Okay, I catch most of George's speak. Let's have all those questions at the end. Okay, we try to have each speaker 8 minutes sharp, so that at the end we have some time to discuss. Okay, now let's welcome the second speaker today, Dr. Qiming Zheng from National University of Singapore.
Can you see my screen?
Start it. Yeah.
Okay. Good morning, good afternoon, and good evening. This is Qiming from National University of Singapore. It's a great honor for me to have this opportunity to share my research. This research is a collaborative research with Professor Wen. In this research, we aim at characterizing different type of urban land changes using nightlight time series data. When we thinking about mapping urban land changes, most of the study in the past few decades focused on mapping urban growth, which is a non-urban to urban land cover change process. However, urban land change includes a wide variety of other land cover and land use change processes. For example, I think you have all witnessed that in urban areas, those old blocks and buildings are being renovated and reconstructed into high-rise and highly dense communities and blocks. So this is a land use intensification process. So to map such a diverse type of urban land changes, nighttime light remote sensing data opens up a new opportunity, because nighttime light remote sensing data can not only map the boundary or the extent of human activity, just as what daytime remote sensing data like Landsat models can do, but the intensity of nighttime light remote sensing data, the brightness of nighttime light, is also a good indicator and an integrated indicator of the intensity of human activity, as well as the intensity of urban land use. So in this study, we use the monthly VIIRS time series from the VIIRS instruments. So to categorize each urban pixels into different types of urban land changes, we selected 30 cities, megacities from the world, which have totally different kind of socioeconomic status and backgrounds, environmental settings, so that our result could be robust and our findings can be generalized into other cities. Here I present the general framework of this study, which includes two major parts, time series modeling and urban change mapping. By integrate these two part of method, we then can identify we then can categorize each pixel into one of these four urban land change types. Due to the time limit, I'm not going to every detail of the method. I will just pick up the core idea and present the main results in the following slides. So in the first step, we propose a logistic and harmonic model to fit the nighttime light time series of each pixel. By using this model, first we can separate the temporal trend of nighttime light change from the outlier and ephemeral signals, as well as the disturbance of nighttime light caused by the seasonality effect of vegetation. Second, by using this time series model, we can determine whether the nighttime light intensity of the pixel is increased or decreased significantly. Here is an example of the time series modeling fitting results. We can see that no matter what the shape or the pattern of the nighttime light observation is, we can have a robust and satisfying fitting results. In the next step, we utilize the fitted curve and extract temporal features from the fitted curve and integrate these temporal features with random forest classifier to create monthly urban maps. We also utilize the unique character of urbanization to develop a new tricks to improve the efficiency of urban mapping. I'm not going to detail about this. As a result, our proposed classification method and scheme creates a high accuracy urban maps at a monthly basis. So then we integrate the information from first, whether the nighttime light brightness of a pixel is increased or not from time series modeling, and second, whether the land cover of this pixel is changed from monthly urban mapping. We integrate these two information to determine or say to categorize a pixel into one of these four types. For example, if the nighttime light intensity of a pixel is increased or decreased significantly while its land cover remains unchanged, we then categorize this pixel into either urban land use intensification or urban land use degradation. Or if the land cover of this pixel is changed into, for example, from non-urban to urban, we then categorize this pixel into urban growth or deurbanization. So here I present a close inspection of the results. Let's look at the upper middle panel. This is a typical example of urban land use intensification. As we can see from the blue curve, which indicates that throughout the study period, the nighttime light brightness of this area is increasing. However, if we look at the Google Earth image, we can find that this place stay as a built up area throughout the study period, but it was initially a factory, and then the factory was cleared out and turned into a school and with some residential and commercial area around it. So this is an example of urban land use intensification. That's how we identify different type of urban land changes. Here I present all the results for 30 selected megacities. The black and blue pixel, black and green pixels indicate pixels has urban growth and deurbanization, while the blue and red pixels indicate urban land use degradation and intensification, while the darkness of the blue and red color indicate the magnitude of urban land use intensity changes. And we found that over 50% of urban pixels have somehow gone through either land cover or land use change. While we surprisingly found that changes in urban land use, particularly the intensification of urban land use contributed to a dominated proportion of urban land change types, urban land changes. We then compare the condition between cities from developing countries and cities from developed countries. If we look at the lower left panel, those are the cities from developing countries. We find that there are a lot more red pixels and a lot of pixels in dark red, which indicate that cities from developing countries have a higher proportion and have a higher magnitude of urban land use intensification. And in summary, in this study, we proposed a new method to categorize a pixel into different types of urban land, different kind of urban land use types by integrating time series modeling and urban mapping. And we found that urban land use change is quite a prevailing phenomenon, particularly in the cities of developing countries. The implication of our study is that we provide a new dimension of describing how the urban land is changed. And by using our model and method, we can have a better understanding of urbanization process, which can facilitate a better modeling and understanding of the impact of urbanization on the natural ecosystem and urban climate. So that's it. That's my research.
Thank you, Qiming. Okay. Now let's move to the third speaker of the section, Dr. Rajaska from National National Institute of Urban Affairs in India. Okay, welcome, Mahesh.
Thank you, Professor Wang, and good morning, good afternoon, and good evening, everybody. It's a pleasure to be part of this particular panel for multiple reasons. One being that after a long time, I'm part of the panel of my professor and guide, Professor Wang. And it's also interesting to present in such a session. Unlike other research things, what I'm going to take you through is the action research, which is currently undertaking in India across the urban areas. So we all know that there are several acute shocks and there are a lot of models in terms of hazard risk models and also vulnerability assessment models for these flooding, sandstorms, and extreme cold and disease outbreak. But what cities are facing across the Southeast Asia and also more specific in India is the chronic stress. They are facing problems related to traffic, problems related to water management, aging infrastructure, and so on. How do you come up with something which can not only address the future climate change, but also take care of the current investment which the Indian government is doing in terms of the infrastructure? So when we look in terms of the extent of investment which has happened in the last 10 years and which is going to happen in the next 20 years, it's quite substantial. So it's not only taking care of these infrastructure for the acute shocks, but also these chronic stresses, so that whatever investment is getting into play is more sustainable and it is also more climate informed. With that in mind, the Climate Center for Cities, or also known as the C-Cube, was instituted by the National Institute of Urban Affairs with support from Ministry of Housing and Urban Affairs, which I represent. And it was done during the pandemic last year. Even though the idea was conceptualized some 3 years back, and there was a huge parliamentary process which led to the financial allocation to drive sustainable development goals and also to create a framework, action research framework through which cities and city officials and also other stakeholders could share their knowledge, practice, tools, technologies, data, to foster development and also to scale up climate action, not only across the 100 smart cities, which the government is currently promoting, but also to the 4,000 plus urban local bodies which are currently in India. Some of the key challenges, I don't want to go into the depth of these things, but it's pretty much common in many of the Indian cities. It is the quality of the data, the collection system, the mechanism, the standards. But more importantly, much of the data is collected and maintained by urban local bodies, and they have a kind of a hesitation to share this kind of a data with larger set of public and also with research institutions for multiple reasons. One, they will be questioned back in terms of the quality, and they don't have an internal quality control mechanism. And the second is much of the data is also available in the paper-based format, where it usually is very difficult for research institutions and also to other stakeholders, especially development agencies working in this particular area of climate change and sustainability, to take or to do analysis and to provide support for informed decision-making process. So how do we overcome it? So we came up with a very ambitious goal of trying to monitor 28 different indicators, key indicators, across 96 data points over 5 thematic areas. And this thematic area includes urban planning, green cover, biodiversity, energy and green buildings, mobility and air quality, water management, and waste management. How can city monitor all these data and monitor these data in a manner that it could help them take informed decision at a much frequent time interval, and also help them develop appropriate policy and overcome some of the challenges which they face on a day-to-day basis. And even though it seems quite simple, it is from if you look in terms of much of the data set, 50% of the data set is highly point-based and attribute-driven, and several other databases are could be captured through remote sensing imageries or time series imageries through drones and other aerial vehicles. But also there is a huge amount of data where we don't have any clear picture. For example, air pollution and air quality. Even though many of us know that Delhi is having a very bad air quality for several years, but the number of sensors which are available in Delhi are quite limited. It is 36. So it's also to promote innovation, and how do we also involve stakeholders, not only research institutions and government organization, but also development agencies, private sector, and also people at a community level to start reporting on multiple data sets to take informed action. So with that in mind, we have a planned picture of urban data observatory, even though it is it's at a much early stage. I'm happy to inform that 126 cities covering over 150 million people are currently providing services to 150 million people reported on this particular framework. And we have collected 96 data points ranging from remote sensing imagery, spatial maps, attribute data, time series data, and also certain plans and actions where cities can use to help move forward in this particular direction. And this includes multiple things, right from economy to how do we maintain heritage and infrastructure. I'm just going to take you through one of the case studies or use cases which we have conceptualized, especially to cater to the water management. Of course, water scarcity is much of a concern to these growing cities, and with Cape Town recently experiencing challenge, there was also another city in India, Chennai, where I'm originally from. In 2018 and 2019, they went through a severe drought, and the drought is not because they didn't get a sufficient amount of rainfall, but basically they were not able to conserve, save, and also take care of their system. So how can we use an high, high intensity time series imageries to look and monitor these catchment, and how these catchment level information can feed into day-to-day municipal corporation information and also to communities? How can this be informed to city level, citizens, so that they can start conserving in a much better manner? But the idea is to go beyond that. The idea is to bring the data observatory concept from state government level to central government level to big data providers. We are also in talk with Google, Facebook, and others to how we can capture the social media data. We are working also with the educational institutions, not only for doing some research and analysis, but how can you promote the attitude of data collection and data analysis amongst municipal officials? So it also includes training and capacity building. And this is an initiative, even though taken by the central government, we have more than 50 partners contributing to that particular initiative. And this partnership is currently growing. And we supported more than 120 cities, to be more specific, 126 cities in the last 1 year. When the COVID was happening, people were also collecting data to inform sustainable practices, and of course to also take care of, also to understand the health. More than 1,000 plus officials were trained in the last 1 year, and we are hoping to create a much better ecosystem for decision making, especially for policy makers and also urban managers, and at the same time using the same amount of information to report on ease of living standards, resilience guidelines, and sustainable development goals. With that,
Okay.
Thank you.
Okay.
Thank you.
Yeah, the time is up. Okay, thank you, Mahesh. We going to have questions later on, okay, after the session is over. So now let's welcome the fourth speaker, Ms. Ying Lin from Chinese University of Hong Kong, and with her Professor Hong Shenzhan from University of Hong Kong. Okay, let's get started.
Yes, can you see my screen? Hello, I'm Lin Yingyi, and I'm from the Chinese University of Hong Kong. My presentation topic today is Annual Dynamics of Impervious Surveys in China at 30-meter resolution derived from multi-source satellite images over the past 3 decades. The urbanization process in China has been significantly expanded since 1978, and as of 2020, the urbanization degree in China has reached over 63%. So the urbanization in China can be defined as the increased number of cities and the expansion of urban space, and also the population growth and the extension of urban infrastructures. So in different scenarios, the urban spaces has been significantly increased, and specifically the impervious surface has also expanded. So monitoring the impervious surface can be as an indicator of the urbanization process, and which can also support the sustainable city development in the SDG 11. So the anthropogenic impervious surface is related to the artificial materials that are impermeable and includes the dense buildings and transportation systems. It can demonstrate different socio-economic and environmental properties, including the urban heat island, non-point source pollution, and urban flooding. However, monitoring the large-scale impervious surface at the in China is difficult, for China covers a diverse climate region and also has complex terrain and also has diverse land cover diversities. So single source data may not sufficient for the impervious surface mapping, and which urges for the multi-source data to support. So in this study, we want to address the following two research questions. The first is how to accurately extract China's annual impervious surveys using the multi-source satellite datasets, and also what are the annual patterns of the AIS over the past 3 decades. We chose China as our study area, and it has large sea land and the north-south difference, and has complex and diverse climate regions. And here are our data sources, including the Landsat night timeline data, Sentinel-1, and SRTM. We use the data according to their data availability, and Landsat data from 1984 and night timeline data includes the DMSP and VIRS. And the SAR data is the Sentinel-1 GRD data. Here shows our overall framework. We performed our analysis on the Google Earth Engine platform. And first, we want to, we use the night timeline data and the SRTM slope data to generate the potential AIS area. And then in this area, we will use, in the period of 1986 to 2013, we used the Landsat data, including its spectral data, spectral features, and the vegetation index. And from the time of 2014 to 2020, we will use both the Sentinel-1 data and the Landsat data. The Sentinel-1 data includes the VV backscattering coefficients and also the GSCM texture features. And random forests are used in this study. After we got the classification results, we will conduct a temporal filtering, in which we assume that the urbanization process is irreversible, so the impervious surface cannot change back to the pervious surface to keep the time consistency. So here comes our results. First, we want to test whether SAR features can contribute to the AIS extraction. And as we can see in the final column, after the integration of the VV backscattering coefficients and also the texture features, it achieves the highest accuracy. And also we test the texture neighborhood size and also the random forest tree numbers. We can see that the accuracy decreased along with the neighborhood size and increased along with the random forest tree numbers. And this slide shows the accuracy across the whole time period. As we can see, the overall accuracy is higher than 80%. And after 2014, the integration of SAR data ensures higher accuracy in the AIS extraction. And we further compare our results with the existing products. And as we can see for the GHSL, it will usually lead to underestimate the urban settlements in the rural area, while the GSC30 will lead to overestimate the impervious surface in the urban center. So our results can keep good performance in both the urban area and the rural area. And also for the other scenarios like the mountainous area, delta and deserts also keep good performance. And here shows the AIS distribution in different parts of China, and we can see the rapid growth of the impervious surface. And Beijing, Shanghai, Chongqing, and Guangdong are chosen as comparison. We can see for Beijing and Shanghai, it is expanded from the center to the surrounding area, while for the Guangdong, it is like expanding from multi-center. And for Chongqing, it is rapid growth have been seen in the recent 10 years. So we further compare the area change at different scales, including the national scales and the provincial scales. And as we can see on the right-hand side, for Beijing, Shanghai, Tianjin, and Chongqing, they are all the municipality. So we can see the previous 3 cities are very similar in the 35 years, and Chongqing is rapid growth is after 2010, and it is the transportation hub which can link the central part and the western part of China. And for the Guangdong, it has similar growth pattern with that of the national level, and Tibet for showing that the western part has lower impervious surface area. And we further compare the results of the 371 cities, and we can see that Beijing took the lead in the four periods. And also the capital of the different province has, the rank has moved forward. And the continuous impervious surface growth has been seen in the 4 periods. So in this study, we first generated the annual high resolution AIS and the national scale using multi-source data, including Landsat series, Sentinel-1, and night timeline data. And we can see that SAR can improve the time series AIS classification. And also China has seen a rapid and continuous growth of AIS in the past 35 years. So that's all for today's presentation, and thank you.
Thank you, okay, for Yin's presentation. Now we move to the final speaker of the sections. Okay, Dr. Mattia Marcosini and Thomas Ash from German Space Center. Okay, Mattia or Thomas, let's get started. Okay.
Yeah, okay, perfect. Sorry, I had to unmute myself. Thanks a lot, Kiao. I hope you see our screen. So yeah, let's keep it short. So we have understood also from the previous presentation that urbanization is happening, and somewhere it has gone really crazy, as in here, for instance, in La Paz, Bolivia. So monitoring urbanization is really important, and that's why we work at the German Aerospace Center, DLR. We recently launched the World Settlement Footprint, WSF, which is a novel suite of open and free high spatial resolution global products aimed at supporting comprehensive analysis of urbanization. And the WF suite has been developed with the support of the World Bank, the Google Earth Engine team, and ESA, and aims at helping to understand the phenomenon and acting accordingly before this happens in order really to foster sustainable development. So the first layer that was completed was the WSF 2015, a 10-meter resolution mask outlining the 2015 settlement extent that has been derived by jointly exploiting multi-temporal radar, namely Sentinel-1, and optical, namely Landsat 8 imagery. And as you can see here from the picture, one can already have a feeling that besides the major centers, it's really detailed also in the suburban and the rural areas where still half of the global population is living. We really took care a lot of having a high quality product. And this layer actually really proved to be the most accurate existing global layer based on quality assessment, where we use 900,000 validation sample that has been labeled by crowdsourcing photo interpretation of very high resolution imagery. And the layer is available actually at the moment on the Figshare repository. Here we see, for instance, a screenshot of Cape Town, and one can appreciate also at this level, at the zooming level, how accurate the product looked like. But we are still talking about 2015, it's already 6 years ago. That's why a couple of years ago, we really started aiming at, let's say, updating the layer and further improving it. Specifically, thanks to the coming of Sentinel-2, we replaced, let's say, this Landsat 8 with Sentinel-2 data, which are available, as we know, let's say, with a revisit time of 5 days since March 2018. And the resulting layer is impressively even more accurate. So it was even beyond our original expectation, and you can have a feeling having a look in the box outlined with the yellow color. And we conducted, in this case, also an intense accuracy assessment that was based in about 780,000 validation samples, still with the help of crowdsourcing. and results fresh from the oven really confirm that this layer is really, say, outperforming all the others and even improving the accuracy of the WSF 2015. But we are not just hearing of, let's say, outlining where settlements are. We have seen also from previous talk how important is to estimate imperviousness. And in this case, actually, we focused on estimating per pixel at 10-meter resolution the percent impervious surface, which is generally a good proxy for building density and is of a really high support in several applications like population distributions or risk assessment or the characterization of the urban Italian phenomenon. So this product, let's say, is completed, let's say, produced globally, and at the moment we are really putting a lot of effort in, let's say, completing a thorough accuracy assessment. And let's say, in addition to this, we are now targeting population. We know that it's one of the key inputs also in several applications, and it's really fundamental for implementing, for instance, efficient government policies, and of course, in turn, allocating resources, planning intervention, or quantify really the number of people at risk. So here, the basic idea is to exploit the imperviousness that I said before, being a good proxy for, let's say, the density. And we use it for distributing, let's say, figures that are available, for instance, from census data or UN World Bank estimates at a certain district level. And here you can really appreciate, still in the case of Cape Town, how detailed this population map can be with respect to other existing available layers, like, for instance, WorldPop. Okay, I mean, to understand the urbanization, it's really important also to characterize how it occurred. So we also took care of having a look to the past and generated the WSF evolution currently available from 1985 to 2015, which will be further, let's say, updated to the current year. And this is a data set that outlines really the settlement extent at 30-meter resolution on a yearly basis. And it has been obtained with the support of the Google Search Engine team by processing the entire Landsat 5.7 archive, meaning more than 7 million scenes. And also in this case, we just completed a very tough validation exercise where we even raised the number of validation samples to 1.2 million. And I have to admit really that the quality is really outstanding. So there will be a publication that dedicated to this. And one besides the animation can also appreciate, for instance, in the case of Sacramento, how the urbanization took place. So really patchy, in this case, really bulky, meaning that, for instance, there was a master plan behind with respect instead to other type of urbanization. And let's say on top of that, now we are really trying to estimate globally, let's say, the imperviousness on a yearly basis, still at 30-meter resolution, and this will enable even more advanced analysis. This is the case of Johannesburg in South Africa. And for instance, one can appreciate in the blue circles these three townships, namely Soweto, Tembisa, and Vosloorus, where the result of apartheid is really clear, for instance, because Black people has been evicted out of the city centers before the 80s. And this township really saw a massive densification over 30 years with respect to where white people live, for instance. So now I leave the floor to Thomas to complete.
Yes, thank you, Mattia. So now finally it's on me to introduce you one of the latest members, let's say, of our WSF suite, which is actually the WSF 3D. So as the name already implies, now we also aim at tackling the third dimension, so the vertical expansion of the settlements, which is an information that so far is not available at global scale, at maximum, let's say, for countries or larger regions. So with this analysis, we used height information of the digital elevation model of Tandem X, which shows a 12-meter resolution. This has been or had been collected in the year 2012. So it's not completely up to date, but all our tests show that it's still quite useful and valid, even if you go for nowadays extent of the urban area. So, and here you see two examples. In the top row, it's Tokyo in Japan. So on the left-hand side, we see one of the various layers that we derive in the WSF 3D context, which here describes the building fraction. So at this resolution, or at this product stage, we have a resolution of 90 meter, again coming from the 12 meters. So we do kind of a zonal statistics per 90 meter cell. So here we estimate the percentage of buildings within each 90 meter cell from 0 to 100%. And on the right hand side, you see again for the same 90 meter cells an estimation of the volume, so which is a product of the building footprint and the height that we estimated. In the lower part, you see again an example for New York and for the fraction and the volume. And again, here one really can appreciate the additional information content that comes along with considering the third dimension. So especially for describing densities, etc., this is a very valuable product. So in the next view, you see again another example now from Cairo. So we have this data set available already globally. And here at first glance, you can already see and explore this third dimension and the distribution of the vertical structuring within the cities. So with that said, let me come to the conclusions. So basically, of course, we see that the WSF suite is a collection of novel data sets that provide accurate, area-wide, and also frequent information on the extent, the morphology, and also the density of build-up areas, but also on the distribution of population. And so with this, of course, we are sure that this data set or suite can become an asset, let's say, for a broad spectrum of users and user communities, especially those, of course, being active in the context of the Sustainable Development Goals and the new urban agenda. Of course, you might be interested in the milestones for the production of the layers. So as Mattia already mentioned, the WSF 2015 has already been completed and can be downloaded and accessed open and free. The next data sets to be released are the WSF 19, the WSF Evolution, and also hopefully in the next month, the WSF 3D.
Thank you, Thomas.
Followed by the imperviousness population data sets and the imperviousness evolution. So thank you for your attention.
Okay, thank you, Mattia. Thank you, Thomas. And now all the speakers have finished the talk. Now, since our session is a little bit late, okay, I want to make an announcement that our section, okay, our group, the Global Urban Observation and Information Initiative, our group has been invited to participate in meetings in this September 6 to 8 for the first international forum on big data for sustainable development goals. They're going to happen both physically and online in Beijing. And so we're going to have 3 hours there. So that's very good. Okay, this time we only have 1 hour. So next time we have 3 hours, so we can definitely have a longer time for speakers, for each speakers, and also for the discussion. Okay, so this is the first thing I want to make you aware. I'm going to send out the detailed information to everyone after the meeting, after this meeting. Okay, so are there any other questions? Are there any questions for speakers?
Yeah, I actually got one for George.
Is George
All right.
still here? Okay.
Yeah, I'm here.
Can you see the chat box? I already text the question
Let me
into.
see. Yes. Okay. Let me read this one. Oh, you can read this one.
Yeah, I mean, as far as I remember, that you mentioned that the LCMAP project, one of the aim of the LCMAP project is to predict future land cover or urban maps. Is that correct?
Yes, that's one of the LCMAP. That's called the P. P is for the projection for the future growth. Yes, that's still in our LCMAP objective. And the only thing right now is for that projection, we need have enough data to support the projection work. And right now, we already conducted some initial test work. For example, in the eastern side, the initial projection already conducted for the Delaware watershed area. So that's already make some projection, and also in some central U.S. In the agricultural covered areas also conducted some projection. So that's just here and there, but they haven't got the national projection yet, because that's very heavy, and so they wanted to use this initial 2 study area result, and also right now select this as the third one, and then they're going to conduct the national projection. That's projection including the urban land.
Oh, okay, thanks, George. I think this is a great product. Really looking forward to the final national level product.
Yeah,
thanks.
Thank you.
Are there any other questions for speakers? Okay. I know it's getting pretty late in Beijing. Anyway, I think that all the presentations, I think, is really impressive and tied to this global urban observation, our initiative. And so, no matter in the global levels or national levels, we have a lot of things to do, and we also see a lot of progress here. And through today's presentations and exchange, so I hope that this kind of activity can continue. And we have different venues. If we have opportunity, I will announce. And another goal for this group is that we want to recruit more people. If you see any other people are interested in joining our activities, and let them send me an email, okay, so that we will be able to have a bigger group. I think on September we definitely will expect more people there, okay. So, so we have with this, we have this 10 minutes over this, and considering that there's another session coming up in 10 minutes. Are there any questions from anyone that you want to discuss before we all go away? Okay, thank you very much for all the speakers. Okay, I think that you've done a great job. Okay,